we can start our next lecture on KKT condition-based outer approximation. So, and you might think that I'm doing this analog because I didn't prepare lecture slides, but the slides are actually online. So if you want to, you can follow the slides online, find mistakes, and shout them out to me as I'm lecturing. Okay, so we are going to now apply the KKT conditions that we just learned to a mixed integer nonlinear optimization problem. And I'm going to write it in the form where we minimize over x, our continuous, y, our integer variables, and eta, an additional objective variable. So I have this objective variable so that my constraints, my objective function now becomes part of the constraints. Okay, and if you recall, I can just do this, because I'm minimizing, I will always push eta towards its lower bound, which is f of x, so I can just pull this objective back up here if I want to do. But writing it in this way turns out to be convenient for what we're going to do. Now, you should recall, let's do this here, from an earlier lecture that a function h that just goes from, Rn to R is convex. One of the definitions that we had was if and only if I have 2 points and I evaluate if I take a first order Taylor expansion of h of around a point x1, then I get this following term. x0 minus x1. And the value of the function is no less than the Taylor expansion around this point. So the picture that you should have in mind here on this slide is that a function is convex if I pick a point x1, I do a linear Taylor expansion around this point, so I get this line that corresponds to the right-hand side here. And then if I evaluate this line at another point, x0, then the function value lies above my line. So my line is a supporting hyperplane. And we're going to use these supporting hyperplanes in our algorithms. And we're also going to say that this mixed integer nonlinear problem is convex if and only if both the functions f and g are convex in Rn cross Rp. So I need to form the relaxation of my integer set to define this convexity. And this one here, this is the problem min-low that we're trying to solve in this lecture. Okay, good. So, so convexity allows me to now create underestimators or outer approximations of my constraints. So for these two functions, what they look like. I'll just write them down here. The blackboard doesn't cooperate, but I can write down an outer approximation, and I'm going to do this around a point x hat, y hat. And I get these two inequalities. So there's first in f is f of x hat plus the gradient f at x hat times xy minus x hat y hat, and 0 greater or equal to g hat plus grad g hat transposed x minus x hat y minus y hat. Okay, so this is just applying a first order Taylor expansion to these two functions here, or the nonlinear functions. I'm not expanding a linear function. If you did expand a linear function, then you get back to the same function. So I would just have to waste a lot of chalk. So I don't like to do that. So those two constraints at any point are a polyhedral relaxation of the feasible set of my mixed integer nonlinear problem. So this is a polyhedral or linear relaxation of the feasible set of my mixed integer nonlinear optimization problem. Cool. Picture. Anybody like to see a picture? Let's do a picture. So let's sort of improvise a picture. We'll have two variables, x and y. Y is an integer variable, so that means my feasible set is going to be a subset of sort of the integers that go along here. 1, 2, 3. Add 0 to it. And then I can have a nonlinear constraint. So we can just do this is looks almost the same, so I'll take a different color, try to trace that out. There's a nonlinear constraint. It's an inequality constraint. So in this region here, we have 0 greater or equal to g of x and y. And now if I pick any point, I can take any point I like. It could be a point inside the domain or outside the domain. But for example, we're going to be interested in points that are feasible points that just lie on the boundary of the feasible set. They're going to be our points that we're interested in. And if I do a linear approximation of this function here, then this is an outer approximation, a supporting hyperplane of my nonlinear set. Okay, and so if you look at this long enough, you can skip the next 3 lectures because this is outer approximation. So all you need to think is, okay, I'm going to find this point, put in a hyperplane, find another point, put in a hyperplane, find another point, and put in a hyperplane until I'm done. That's it. Very easy. So this was 1.5 hours of outer approximation in one sentence. But we also want to prove things, so there is something called the optimality lemma. And so for that, I need to introduce a new problem, a nonlinear optimization problem that depends on a particular choice of my integer variable. So I'm going to put a y hat in here. Bless you. And this problem is going to be a minimization just over x. I'm going to cheat a little. Well, I'm not going to cheat. I'm just going to pull the objective back out just because it saves a little bit of chalk. X, y hat subject to g of x less than or equal to 0 and y hat. So y hat in this case is fixed. So think of it in this picture here, y hat is equal to 3. I fixed my integer variable to 3. Okay, and then I want to solve this problem. And there's the following optimality lemma that we're going to prove. Okay, and the lemma says that I need a label, so I'm going to label these constraints here. I'm going to call them the linearization around y hat. So there's also a y hat here, it's just not orange, it's white. So, if x hat solves or is the solution of the nonlinear optimization problem in which I have fixed y hat, then it follows that, and I can't do that, so then it follows that for y equals to y hat, what do I want to say? And any x that satisfies these constraints L of y hat, the linearizations around this point, x hat solve NLO. I need another then here. Sorry, this is not a good then eta is greater than or equal to f hat. Okay, so what does that mean? That means that if I have this linearization and I look around this point and I look at my set of linearizations here, then the optimal value of this NLO was f hat, and inside with the linearizations I cannot find a better point, so I cannot find a lower point. This will become clear in the proof. So I'm going to do the proof, and then you can reword the lemma, and it'll become easier to understand. So what I'm going to do is I'm going to take these two constraints here, and the first thing I'm going to do is I'm going to substitute y equals to y hat in L of y hat. And if I do that, so if I, just for a moment, if I put a y hat here and here into these constraints, then the second part of this gradient will just disappear because y hat minus y hat is 0. Okay, so I'll just undo this real quick. So we get, we get two sets of constraints which are slightly simpler, namely eta greater or equal to f hat plus the gradient now only with respect to x of f hat, x minus x hat. So the constraints are going to be in x only. And then I'm going to do a trick. I'm going to now sum these two constraints. I'm going to add them up, and I'm going to weight. So the first one, I'm going to take a multiplier 1, and here I'm going to take the multiplier lambda hat, which is the optimal multiplier of my solving my nonlinear optimization problem that we had up here. So the nonlinear optimization problem here has a solution that's x hat and lambda hat. And if I do that, then something miraculously happens. I get eta greater or equal to f hat plus lambda hat transpose g hat plus, and now I'm going to get a gradient term here, which is grad x f hat plus grad x g hat times lambda hat, all transposed x minus x hat. Okay, so who remembers our favorite KKT conditions from about 20 minutes ago? If you do, then you will notice that this term here, or if you look it up, is 0 due to complementary slackness. So that's nice. And this term here is also 0 because of the first order condition. That's just the gradient of the Lagrangian. So our optimality conditions give us that eta is greater or equal to f hat, independent of what x I chose. So in other words, what these constraints do is they ensure that the linearization is strong enough so that you cannot find, for the same y hat, you cannot find a better x in your linearizations. So these are, so there's maybe a corollary here, and that makes it maybe clearer. Let's see if I can formulate this clearer. If we put y equals y hat into L of y hat, then eta is greater or equal to f hat. In other words, there is no better x point. And so, and f hat, of course, was the optimum of the nonlinear problem. So this linearization behaves just like the mixed integer nonlinear optimization problem. If you put y hat in here and solve this nonlinear optimization problem, which is really hard, then what you get out of here is x hat, lambda hat, and f hat, the value f hat. Now, if you just put y hat into this set of inequalities, then I have a proof that says the objective function value cannot be lower. And that's key in proving convergence of outer approximation later. Okay, there's a similar lemma to this called the infeasibility lemma. And that has to do with the fact that nonlinear optimization solvers or nonlinear problems are not always feasible. So NLO of y hat may not be feasible because it's a nonlinear optimization problem. And in that case, we solve a nonlinear feasibility problem, a nonlinear feasibility optimization problem around y hat, which has the form, or one example of such problems. There's a lot of different problems. One of them has the form: minimize the sum of gi of x and y hat over a set I, which I will define in a moment, subject to gi of x and y hat less than or equal to 0 for another set I in F. And these sets are where I is the set of all indices I such that gi of x hat and y hat is positive or infeasible. And F is simply the complement. So that's the set 1 up to M without I, or the set of feasible constraints. And the nonlinear optimization solvers will choose these sets for you, and it's not unique. So a little picture here. I'll just do this really quick. You could have two convex constraints. So one convex constraint is over here. And then there's another convex constraint that is over here. And if you want to be in the intersection of these two constraints, you're out of luck. And the nonlinear optimization solvers will converge to a point that lies on the line that is orthogonal to both of these curves here. So the solution to this problem, if we solve it, this will give us a solution of NLFO of y hat is x hat. We again get multipliers, and this solution is any point. In this case, any point along this line would be a suitable solution. So it's not unique, the solution, and it depends on how you set up this problem. Because you have a choice here, I can say, this guy is my feasible constraint, and this is my infeasible constraint. If I do that, then x hat lies here. If I do the other way around, if I say the orange one is feasible and the blue one is infeasible, then I'm over here. But there's also a possibility of actually saying both of them are infeasible, and then you get points along the line. Most solvers will go to either one or the other point. Okay. And then, like the optimality lemma, there's an infeasibility lemma. And I just write the lemma down. I'm not going to prove it, but the proof uses the same trick. So here's the infeasibility lemma. So we let x hat solve the nonlinear feasibility optimization problem around y hat. Then it follows that do this. So that's that, and consider the outer approximation. So I'm starting to use words that you'll hear more in a moment, which is 0 greater or equal to g hat plus grad g hat transposed x minus x hat y minus y hat. And then it follows there exists no x such that this constraint, which is now the linearization for the feasibility one at my point y hat, such that LF of y hat is feasible for y equals to y hat. And the way you prove it is exactly, it's very similar to what we did in the other part. So you plug y equals y hat into here, and then the second term will disappear. So you now only need to look at the gradients with respect to x. And then you use the fact that you solve this problem to optimality. You now have a different KKT condition, but these terms here, very important, these guys here are strictly positive. And so amongst these constraints here, there are some which are strictly positive. And so when you plug in the gradient condition, you find that the gradient will vanish, and you're left with something that says 0 greater or equal to something that is greater than 0. So 0 greater 0 is a contradiction, and that means there cannot be a feasible point. That's the proof of the infeasibility lemma. And so as a corollary, again, when you add this constraint, then the linearized problem behaves like a nonlinear problem. So the nonlinear problem tells you this is not a good point, it's infeasible. When you linearize this problem, it tells you again, this is not a good point, it's infeasible. So what we've done here is today, we've shown that these linearizations, if we do these linearizations about optimal points of either the nonlinear optimization problem or a nonlinear feasibility problem, the optimal points that we get out using these linearizations tell us exactly the same information about optimality or feasibility as the mixed integer nonlinear problem. And now we have an algorithm. So everybody can now, as an exercise, write down an algorithm for solving mixed integer nonlinear optimization problems. All you need to do is solve nonlinear optimization problems, collect linearizations, and keep doing that, going round in some loop or something. That's it. That's a very simple algorithm, but it works. It works really well. And it's the basis for a lot of more successful methods that we'll talk about over the next week or so. So apologies for going over time. The lecture notes are online, so you can see that, and you can see the proof, and it looks much cleaner there than it looks on here, but I wanted to try this out, and I really enjoyed working on a blackboard for a change again. So thank you very much. And